Okay, welcome everyone. Today it's a pleasure to have Alex Belin from CERN, who's going to tell us about gravitational path integral from TT bar, or should I say T squared deformation. So please, Alex, take it away.
Great. Thanks a lot for the invitation. It's great to be giving this talk today. I'll be talking about a paper that came out earlier this summer with Gabor Sorosi, who's also at CERN, also giving a talk next door, actually. And Aitor Lefkovich, who was at Stanford at the time, but now has gone on to other ventures. So before I get started, let me just start with a couple of disclaimers. Well, the first one is, I try to say it at the beginning of any online talk, really please ask many questions, interrupt me frequently. It makes it a lot funner for me and hopefully for you guys as well. So really don't hesitate, and let's try to keep this informal and interactive. The second, which is related to this, is because I'm using a cable and I've never really done it before, it could happen that things stop working at some point. So if they do, please also interrupt me and let me know that you can't see what I'm writing. And the third one is more physics related, is that I've given this talk a few times and there's several aspects of the paper that are a bit technical. And the first few times I gave it, I maybe focused a bit too much on the technical details. So today I'm going to try to do a bit less of that. Also because I think most of the people in the audience are more interested in the applications to extremal volumes and complexity. So it's possible that I stripped off too much and that it'll make it even less understandable. So if at any point I'm not technical enough, please stop me and ask questions. Good. So the punchline of all of this is just stop me and ask questions. Good. So let's get started. So you know, ADS-CFT has been really a super powerful tool to study quantum gravity. You know, really part of this comes from the fact that, you know, the dictionary of ADS-CFT tells you that the asymptotic value of bulk fields gets mapped to local operators of the boundary CFT. And really what's going on here is that the local degrees of freedom of the theory all lie at the boundary. Okay, first of all, they're local. Degrees of freedom are local, and they lie at the boundary. Okay, in particular, the boundary is a place where gravity is switched off. And so, you know, many things are well defined there. So in particular, you know, you can study correlation functions, which are sort of like the ADS version of scattering amplitudes. Your operator insertions are defined here. And again, at the place where the operators are inserted, gravity is switched off, so we know how to make sense of this. You can also study more fancy things like entanglement entropy. But all of these things are really defined in the local quantum field theory, which is the CFT, the boundary CFT. And we know how to make sense out of things. So this is extremely convenient. Now, it's also, I think, fair to say that in some sense, it's also a burden. Because some of the perhaps more interesting questions that we'd like to ask are a bit obscured by this. And this is not going to be an exhaustive list, but of course, some of the questions that one would like to ask is, you know, what are local operators in quantum gravity? Okay, and probably this cannot, probably local operators may not, exactly local operators may not exist in quantum gravity, but what are approximately local operators in quantum gravity? Or how do we define quantum gravity with Dirichlet boundary conditions? Rather than asymptotic boundary conditions. How do we make sense out of that at a full, say, non-perturbative level? And of course, there's many other questions that sort of fall into this class, and they can maybe be regrouped under the more general question is, how do we move into the bulk? Okay, and I think it's been pretty clear since the early days of ADS-CFT that this is very closely connected to the idea of holographic RG. From that point of view, we understand that the IR cutoff in the bulk, or the maximal bulk surface the maximal bulk radius should be related in some way to some type of CFT cutoff. But this relation between the two is sort of schematic. And so part of what we would like to understand better is how to make this more precise. Okay. And of course, throughout the years, there's been a couple of papers that have tried to study this question. There's, for example, two papers that stand out with this respect are a paper by Faulkner, Liu, and Rangamani, and a paper by Hemsterk and Polchinski from many years ago. But there's been sort of exciting progress in the last couple of years, and in particular in the context of ADS-3-CFT2. Which started from a paper by, maybe I should write at least some references, by Magot, Mazet, and Verlinde. Which considered an irrelevant deformation of 2D CFTs. Known as TT bar, which maybe, as Ignacio said, we'll refer to as T squared for reasons that will become clear in a second. And so the idea is to consider the following deformation of the CFT action. We consider deforming the theory by an operator which is built from the stress tensor. And it's important, maybe not always emphasized enough, that this is a sort of iterative procedure, and you define it at every value of lambda. At every value of lambda, there's a stress tensor. And this TT bar operator, we can write directly built from the stress tensor in the following way. Okay, so it's some operator that's built from the stress tensor, that's quadratic in the stress tensor. And it turns out that this type of deformation, even though it's an irrelevant deformation, so this is a dimension 4 operator, it turns out that you can make sense out of this deformation because it's integrable. Okay, so in particular, if you started with yes.
I had a quick question. What is lambda here?
Lambda.
What is lambda here?
Lambda is some parameter that you're going to deform your CFT action with. So you imagine doing something like this. Okay, but it's sometimes more convenient to instead of writing this, to write it in this form, because the operator O is only sort of defined is defined sort of iteratively. This stress tensor here is not the CFT stress tensor. At any given value of lambda, you deform it with the stress tensor of that theory.
Okay, so we are adding some extra field and considering how it varies with the parameter lambda.
That's right, yeah.
Okay. Thank you.
Thanks.
Thank you.
Yeah. So as I said, this is an irrelevant deformation, but you can still make sense out of it because it's integrable, and in particular, the spectrum is known. So if you had a CFT whose spectrum you knew to start with, you do this deformation and you also know the new energy spectrum. Okay, so there's an exact formula, E of lambda. And sort of the very nice observation of Magot, Mazet, and Verlinde is that if you take this function E of lambda, okay, and you compare it to the mass of a black hole, but now not in sort of asymptotically ADS, but in a theory of gravity with a finite cutoff at some given R max, which is related to this parameter matching this parameter lambda, sorry, that you get a very nice match. Okay, and there's of course a lot more in their paper, but this is maybe sort of the most remarkable feature. So because this deformation is integrable, it's irrelevant but integrable. You can sort of make sense out of it, and if you then sort of follow your nose and start comparing this to masses of black holes, you get a very nice match. So that was really promising, and it gave a sort of new perspective on how to think about moving into the bulk, about putting a boundary conditions at some finite value R max. But this is all a story about ADS3 CFT2. So of course it's very natural to ask, well, what about higher dimensions? And this was studied in a couple of papers, first by Marika Taylor, and then in a paper by Hartman, Krudov, Chagulian, and Tajdini. And in fact, it's more the second paper. It's more the formalism of the second paper that I'll follow today. And what they did is they wrote a deformation of higher dimensional CFT, so it's going to look very similar. Where you deform the theory by some operator x. And x is called the t-squared operator. So in higher dimensions, you don't have factorization between left and right movers, so it doesn't really make sense to talk about TT bar. But it's a certain operator t-squared that I'll write down more explicitly later in the talk. And this operator it's not really clear that this operator exists or makes sense in generic higher dimensional CFTs, but for holographic theories that have large n, you always have so-called double trace operators that you can write schematically in the following way. They're defined at large n. And so they considered this particular deformation, and again, did some matching with energies of black holes and found a nice match. Okay. Now, sorry.
Someone else had a question. Maybe can you ask?
Sorry, I didn't.
Yeah, Z here is the partition function of the bulk or the boundary CFT?
Yeah, Z is the partition function of the boundary CFT, or of the boundary field theory, because once you're at finite lambda, it's no longer CFT, it's just a field theory.
Yeah, thanks.
Yeah. Very good. So there's an obvious question to ask here. So I said that this operator t-squared makes sense at large n, and there's an obvious question to ask is, does it make sense at finite n? Is this really a well-defined thing to do? And I'd rather be upfront about this, that I will not touch upon this question in any way today. I will just sort of assume that that this makes sense, or at least that it makes sense in the large n limit, and sort of see what it buys us. Okay. So let me just leave it at that. Okay. So my goal for today is the following. I'm going to be doing really two things. The first is that I'm going to give a new perspective on this deformation. And what I'll show is that the flow equation can be recast as a diffusion equation, as a diffusion-like equation. And what I'll do is solve for the diffusion kernel. And what we'll see, so sort of schematically, solving for the kernel means the following, is that if you consider some partition function for the field theory on symmetric gamma at deformation parameter lambda, is that you can obtain it by integrating against a kernel. And I'll solve for this kernel and show you that it's given by the Euclidean path integral, the gravitational path integral, with Dirichlet boundary conditions on both ends. Okay, so that will be sort of the first part of the talk. And the second part of the talk, which maybe some of you might be more interested in, is to try to relate this to find a CFT way to compute extremal volumes. And actually, this is sort of the way that we landed on this in the first place. Okay. And so maybe I'll just say a few more words about this second point here. So here's a
Alex, before you go on, could you go back?
Yes. Yes.
On the right hand side of this equation, is there also a sum over lambda prime?
No, lambda prime is like a boundary. Well, it's like a boundary condition. So the idea is that you have.
Okay.
Yeah, but there is a sum over metrics.
Okay.
There's a sum over metrics.
Good. Okay, thanks.
Yeah.
Since you've been interrupted, Alex, can I ask a question?
Yes, please.
You've emphasized the idea of Dirichlet boundary conditions, but a while ago, Monica and a collaborator I'm not remembering, I apologize, they had an interpretation where you could reinterpret it, I think, in terms of just more standard double trace deformations of the boundary CFT, where I think you were going to infinity. And so I'm wondering how that story fits in, or if you're going to comment on it, or.
So the quick answer is I'm not exactly sure at this stage. That's sort of the quick answer. Yeah, I think so. So Monica was trying to argue that, yeah, it is more standard boundary conditions, but thought about in a different way. Yeah, I'm not exactly sure.
Okay.
Yeah, the quick answer is I'm not exactly sure, and I'm also not exactly sure if her formalism can be lifted in a natural way to higher dimensions or not. And it's possible that it can't, or it's possible that it can, but I don't know. I don't see exactly how. And because I'll be treating really dimensions democratically here, I'm not going to sort of. There might be special things that happen in 2 dimensions that you don't see in higher dimensions, and so I think the formalism that I'll use will not be able to distinguish that. Okay. But the short answer is I don't know. Yeah. Thanks. Any other questions? Since we're at it. No. Okay. So let me just say a few words about the second point here. So the way to think about it, sort of the standard T-squared deformation is here's the sphere partition function, or a cartoon of it, and you have some radial coordinate r like this, and I guess this is Euclidean time, and so doing the T-squared deformation is sort of moving you on constant r slices. So this would be sort of a cartoon. You move radially inwards with the T-squared deformation. It turns out that for other reasons, we were interested in trying to find a different type of deformation. So basically, if you imagine having some, boundary metric gamma here, you can think about this as the overlap of two states prepared with the Euclidean path integral in which you've put the metric gamma. Okay, so this is also equal to this. But we were trying to understand how to go read off extremal volumes in these states. And extremal volumes sort of lie here. Okay, there's some extremal slice. And we're interested in, trying to capture the volume of that extremal slice. And so it actually looks like the type of deformation you would want to do that if you're trying to access this particular slice from the boundary is slightly different. Instead of moving radially inwards, you would want to do something like this. Okay, so so this seems like it's a different kind of flow. And actually, you can pretty quickly convince yourself that this type of flow will not be just turning on a constant deformation parameter lambda, but rather what you want to know is, can you make sense out of doing a spatially dependent deformation parameter, lambda of x. And actually, this is also related to understanding whether you can do the t-squared deformation on curved space. Okay, so maybe I'll put a question mark. And so those were sort of the
Alex, didn't you just tell us you could do it when you talked about putting it on spheres and moving in radially? In your first picture, aren't you putting it in a curved space?
Yeah. So sorry, maybe I should have well, okay, I was trying to make an analogy between the two pictures, but you're right, is that usually what you do is you put it on, we should really do the point. I mean, the problem is that in 2D, you can go to the cylinder, which is not really curved, so that's okay. But yes, to be safe, I should have maybe drawn this in Poincaré.
Okay.
And in 2D, you can also, go to the cylinder because this is not curved and it's fine. So that also makes sense in 2D. Now I have to draw the circles like this. But actually, even in 2 dimensions, it's not really known if you can put it on other types of surfaces. For example, does it make sense to put it on a negatively curved surface?
Okay.
And I think that's still an open question. So I should say that even in d equals to 2, this is unclear. Okay.
And this may be jumping ahead, but are those slices you're drawing in the second picture, those are hyperbolic slices now?
Let's say they would not have to be. It's going to be very convenient for us to make hyperbolic slices, especially if we're doing it in ADS. But I think in general we were trying to understand whether of this type makes sense at all.
Okay, thank you.
Yeah, thanks. And what we'll see is that our kernel can do this. Okay, with some caveats that I'll get into. But sort of that was the motivation. Good. So that was my introduction. So let me just quickly go through what the plan for the talk is. So this was my intro. I'll start by just explaining how you can relate the flow equation to a diffusion equation. And then I'll solve for the kernel and show how it connects to the path integral. Or at least I'll sketch a few steps on how you do that, and I'll avoid the technical details. And finally, I'll tell you how to connect this to Hartle-Hawking wave functions and extremal volumes. Okay, but this is maybe a good place to stop and see if there are any other questions before I get started. Okay, I guess.
So Alex, maybe before you get started, sorry, I don't know if this is related to the difference that you were alluding to somehow in the d equals 2 case, But in the ADS3 CFT2 case, for instance, if I consider a constant time slice and I consider a disk, and I view the boundary of this disk as the cutoff of your TT bar deformation in this perspective. In the work of Bartek, Czech, and collaborators, or using kinematic space techniques, you would be able to compute the length of that curve using the differential entropy.
Okay.
But as far as I understand, unless you assume translational symmetry, we don't know how to extend. And it's not just true that you can compute the length, but I could interpret this as a volume, as an extremal volume too, using the so-called Crofton formula. So, do you think that the fact that you are able to use the TT bar perspective on this problem in higher dimensions could also provide some light on how to extend this kinematic space way of thinking in higher dimensions, or this is a completely off question?
Let me start by just trying to understand what you said. So you said that you could use the differential entropy to get access to the length of this curve.
Yes.
And then from that, you want to read off the volume inside.
Yes.
By using like some kind of Gauss-Bonnet theorem, or?
Yeah, I guess it's related to that. Yeah, I think that in those papers, they were referring to something that they call Crofton formula, but they have a CFT way of a CFT object that computes volumes in the bulk for you. But as far as I understand, this is only working in 2 dimensions, whereas you are going to tell us how to do this in higher dimensions.
Yeah, so
I'm wondering if somehow your prescription is managing to generalize the picture that those people have.
Yeah, yeah. So the quick answer is, again, I'm not sure how it connects to something like differential entropy.
Okay.
I'm also not completely sure if they can do that if the metric on this slice is not constant curvature.
Oh, you may be right. Yeah, yeah.
So
I was literally assuming yes.
If you put planets or whatever.
Yeah, they wouldn't be able to. Yeah. So yeah. I was thinking about global ADS. Sorry.
Yeah. For global ADS, probably you can do more. But what I'll say in principle, and again, there's a bunch of caveats that we can discuss in due time. But in principle, would give you access to any kind of bulk geometry, even
okay,
if
great. Yeah.
Whatever.
Thanks.
Yeah, thanks. Any other question before I get started? Okay, so let's dive in. So let me just start with the flow equation. So I think it's useful to just write down what the flow equation that Hartman and collaborators wrote down. So like I said, it takes this form, but I didn't tell you a few slides ago what the operator is. So the operator is just the following. It's again a quadratic operator built out of the stress tensor. And it's quadratic in the t's, but it also has some other piece which come from using the holographic counter terms. And I'm putting a twiddle on the counter terms because actually the counter terms that they used is just the counter term, but without the boundary cosmological constant. So you would not write a term like this where Q is the induced metric on the cutoff surface. So the operator is the following, square root of, there's some coefficient here, which is not terribly important. Like I said, Q is the induced metric on the surface. Okay, and oh, I didn't define the big G is the supermetric. Okay, so this is what they did, and they found that this is the deformation that works and reproduces the right spectrum. And Qij is, you can think about it as an induced metric, which is just the following. Okay, so this is the flow equation that they wrote down. But actually, to make connection with the Willow-DeWitt equation, I'm going to consider a slightly different flow, which is simpler, which is just taking the partition function and multiplying it by the counter terms. Okay, so if you want, I'm going to consider the bare partition function instead of the renormalized partition function. And then this bare partition function has a much simpler flow. Oops, sorry. GIJKL has the metric variations. Okay, so all these terms with the counter terms basically disappear, and the flow equation is much simpler. And why am I doing this? This has an advantage that this equation actually has a scaling symmetry. Okay, so you can check that, you know, a solution of this equation would satisfy if you multiply, if you do a rescaling by alpha, and you rescale the deformation parameter in the appropriate way, then you come back to yourself. And so because of the scaling symmetry, it's very natural to make an ansatz for the solution, which is to just consider something that is some combination that's scale invariant, if you want. Okay, so because of the simpler expression, this simpler flow that has a scaling symmetry, you can make an ansatz that will, you can make an ansatz that if you plug that back in, that gets rid of the lambda dependence, and you're left with another equation. And it turns out this equation is nothing else up to some sort of mild field redefinitions, the Willow-DeWitt equation. The radial Willow-DeWitt equation. And what's really nice here is that it's gauge invariant, in that there's only the combination gamma over lambda to the 2 over d that enters. Okay, and so what this sort of shows you is that actually trying to solve the t-squared deformation on a curved metric or doing a spatially varying deformation is actually the same problem. Okay, because it only really depends on the ratio. So if you know how to do it on curved space, then this is no problem. And maybe to come back to Rob's question earlier, in this paper by Hartman et al., they did consider black holes on curved space and understood how to deal with that. Again, always working sort of in the large n limit. So yeah, it's still an open problem to know if it really makes sense non-perturbatively, even in 2D. But sort of just working in the large n limit, you can certainly do this. And so if you know how to deal with curved metrics, and you realize that actually there's this scaling symmetry, you can also deal with spatially varying parameters. Okay. Now this is not, if you want, this is not something that's sort of deeply new. This is sort of working it's kind of working the argument of the Cornell group backwards. But we'll see that it's kind of nice. Okay. Very good. So that was the sort of first point. And maybe I didn't say, but this looks exactly like a diffusion equation up here, right? Where there's one derivative with respect to the, sorry, there's one derivative with respect to the deformation parameter, but two derivatives with respect to the metric. And this term here is like a potential. And this sort of, it was realized a long time ago that the partition function in ADS-CFT, the Euclidean partition function, satisfies the Wheeler-DeWitt equation. But it's a bit confusing to understand how that it can also satisfy a flow equation, because the flow equation is like first order in derivatives, whereas the Wheeler-DeWitt equation is second order in derivatives. But here we sort of understand how this works. It's because the Wheeler-DeWitt equation is only sort of on a constrained set of initial data in some sense. Okay, so those are just some general comments. But okay, let me go ahead and now, so this is some diffusion type equation, and let me go ahead and solve for the diffusion kernel. Okay. So the first step is to note, and this was again mentioned already both in the Magot-Mezet-Berlinde paper and in the Cornell paper, that the flow equation is equivalent from doing the following. So this is called sort of the Hubbard-Stratanovich representation of the flow equation, is that you can introduce some delta lambda. So you can introduce a small metric perturbation if you want, integrate over it. It's Gaussian, as you'll see in a second. Let me just write it like this. Okay, so you can do a small deformation of the background metric, integrate over this Gaussian factor here, and this produces the flow equation for you, okay, in the limit where delta lambda goes to 0. So this is just if you want, it's a Hubbard-Stratanovich way of writing the flow equation. But now what you can do from this is iterate it. You can first iterate it, and then you can take a continuum limit. Okay, so this is the thing that I'll just, so the way to think about it is that, these h's up here, if you expand the z every time and you go to quadratic order in h, you'll just get t squared. So that's sort of the t squared operator. That's where this is coming from up here. And this is here just to generate this Ricci potential in the diffusion equation. Okay, so the idea is to iterate it and then take a continuum limit. So what we do is we do a series of steps that we label by k, and there's going to be so k is the number of steps, and there's a total of, say, m steps. Okay, and so we can define some sort of coordinate that tells us how far along we are, that goes between 0 and 1, which is k over m. And then in the continuum limit, this will just become 1 over m. And then we're going to do small deformations parameter delta lambda k of x. Okay, and it's convenient to rewrite it as 1 over m times some function mu k over m of x. Okay, and so in the continuum limit, this will just become the size of your step times the function mu that encodes the path that you're taking in the deformation parameter lambda of x.
So, can I ask a quick question?
Yes, yes. I can't hear you anymore somehow. Hello? Can other people hear me?
Nope.
Yeah.
You cannot hear me.
No, we
can hear you, Alex.
Hear the
Oh, you can hear me, but you cannot hear the question either. I see.
Okay, so am I audible now?
Yes, yes.
I'm sorry for the interruption. Gamma here is the induced metric on the CFT. Gamma is the metric in the CFT, and H is induced metric in what sense? Meaning it's deforming the metric due to the flow lambda.
Yes.
And okay, and we are integrating over all possible h which is produced due to this deformation.
Yeah, so the idea here is that we start with, I mean, you could start at lambda equals to 0. You have a CFT defined on the metric gamma. And then you can consider defining that partition function where you shift gamma by some h. And then you're going to integrate over the partition function with this particular sort of kernel here. Okay? And you're going to do that infinitesimally in the size delta lambda. So if you want, there's a saddle point equation which becomes exact when delta lambda goes to 0. So h is a small deformation of your CFT metric that you're integrating over.
Is there a general recipe for integrating over all possible h in the CFT? Was I audible?
Yeah, I'm not sure. I'm not sure exactly. It's a function, and you integrate over it. Sort of formally.
Okay. Okay, maybe I can ask it later. Oh, thank you.
Okay, thanks. So what I was saying is that you have this so the total deformation parameter lambda of x that you're trying to achieve, you're going to get to there in a series of steps. And so this function mu just encodes the path that you're taking in this series of steps. Okay, and eta is like a new coordinate that emerges, which encodes where you are in the series of steps. Okay, so that's the idea, and then all you need to do is take this and iterate it and do a couple of changes of variables that I'm going to spare you. But what you can do then is just write down sort of a general metric in the following form: eta x and then you basically just have to relate these functions that appear in your metric according to parameters that you have in the appropriate way. You iterate this, you do a bunch of change of variables, and within this particular sort of gauge that you pick for the metric, you find the following. So we're integrating over sort of metrics at every value of eta, and we do this step by step from eta going from 0 to 1. So in the continuum limit, this just becomes an integral over metrics or over induced metrics with some boundary condition. There's an exponential, which comes from these exponential factors here and here. Okay, so I'm just going to write it as tot of g, z of lambda prime with 2 over d times q to the 1, q of 1. Okay, and what you get for the total action is the following. So now you get, there was already a d-dimensional integral here, but now because we're iterating it in steps, there's going to be a d plus 1 dimensional integral with an additional integral over this variable eta. The full metric okay, plus s rest. And s rests is just minus twice the cosmological constant plus square root of q at the endpoints. Okay, and so I'm skipping many steps, and maybe I've skipped too much, but this is the sort of the pain that I tried to spare you from actually doing this in real time. But the idea is that you have this Hubbard-Srutanovich trick that generates the flow equation. You iterate it many times, you do some changes of variables, then you write down a sort of general metric according to your parameters, and you just find how to relate them. And what you get at the end of the day is the following. You get this expression here, but thanks to the Gauss-Kutaisi equation, this is nothing than the d+1 dimensional Ricci scalar plus 2 times the trace of the extrinsic curvature at the endpoints. And so this whole thing becomes just the Einstein-Hilbert action evaluated between 2 Dirichlet walls with the boundary, with the appropriate Gibbons-Hawking term, which is here, and with sort of the leading holographic counter term. Okay, and I'm going to make a bunch of comments, but I feel like I went very, very quickly, maybe now too quickly. And so are there any questions about this?
I just had a quick question, sir. It seems surprising that at the end, the term in the bracket is leads us to the Gauss-Kutaisi equation. Is it something special about the action which is doing so, or?
Yeah. So maybe I can make already one comment. Is that the Ricci, having this Ricci potential in the diffusion equation was crucial, because if you did not have it, if all of a sudden I remove this, then there would have been no way to combine the extrinsic curvature squared into something that's d+1 dimensional diffeomorphism invariant.
Okay.
So the Ricci potential was crucial to see how you get the k squared term here. Well, it's related to these h squareds here, but you need to sort of change variables and introduce something such that the h's are like the derivative of something else, and so this transforms into the extrinsic curvature eventually. Okay.
Just another question, sir. So h here is obtained iteratively. We first change the modular parameter. We change the parameter lambda and find the corresponding induced metric, and then take the continuum limit of it and integrate over the.
Yes.
Okay. Thanks. Thank you, sir.
Okay. So I went over this a bit quickly.
Actually, before you go ahead, can you? What set the cosmological constant, or what was that? I'm pointing at the screen. Is that a -2 lambda? Yeah.
It's a -2 lambda. Yeah. So you're asking how did the coefficient come out correctly?
Oh no, but what is it? There's a number there. What's the number? Like, it must be parameters in the problem.
Oh yeah, you mean it's like d times d-1 over, is that what you're asking?
Right.
Yeah.
No. Okay, and what set that L?
Yeah, you're asking how did you recover the L ADS?
Basically, yeah.
Yeah, good. So yeah, in some sense, I think the sort of fair way to say it is that there's some freedom in how you do things, because there's coefficients here that I haven't specified.
Okay.
And that were not specified from the get-go.
Okay.
And you tune a couple of them to get the Einstein-Hilbert action. But so in some sense, you could have said we did this by hand. But there is one important point, is that there's more terms here than you have free coefficients. So in some sense, you can get some of them by hand, but the ratios are not tunable. And sort of the nice part is that you get all the ratios to be correct.
Okay, but this is this is really, I can think of this as a quantum path integral. I guess, am I working in a regime where this is a very low curvature bulk? Like, is the Planck scale much smaller than the ADS scale? And if so, where did that separation appear? Is that a question I can ask?
Yeah, that's a question you can ask. That's a fair question. And actually, I'll make a comment related to that. So I think that part is, I see. That part is definitely important. And well, so, okay. Maybe detoured a slightly
a related question, Alex. I mean, does this path integral really make sense, actually?
Well, yeah. So good. It's not, no. So the quick answer is that it's not completely clear. And I think where we use large N is that there's sort of, when you do this quadratic deformation of the partition function, there's coincident terms there that appear, which is basically related to the expectation value of t squared. And now you can ask, how do you know that that makes sense? And that you know that that makes sense because of large N. Okay. Now, do you know that it makes sense at finite N? The answer is, well, we don't. So that's, I think, the answer to Mihal's question. And for the answer to Rob's question, that was sort of, if you want the field theory way to see that large N was important. But you were asking, how did I see that LADS and G Newton, how did they enter here, and how did I see that they needed to be big? Is that the ratio needed to be big? Is that your?
Yeah.
Yeah.
Could LADS be like some, I mean, at this point, some dimensionful number constant that you need to use in your calculation, which will ultimately identify with the radius of curvature?
Yeah, I'm not sure I can give a very sharp answer to this question in real time. I might have to think about it. There's certainly one place where you introduce. Yeah, I think the right way to say it is that you start with a LADS that is 1, but it's 1, and then you introduce G Newton, which is sort of measured in ADS units. And the question is, why do you need to make that G Newton very small? And I think it's related to the fact that you can trust these saddle points here, because basically G Newton is lambda. But I realize that I'm not giving you a very sharp answer, so I have to think about it a bit more.
I mean, it must be related to your large N again somehow.
Yeah.
Yeah.
But yeah, it's true that in real time, I don't see exactly in these series of steps where it was crucial. So yeah, I have to think about it, and yeah, I'll get back to you on that.
So can I ask a question?
Sure.
While taking the continuum limit, we are taking m to infinity.
Yes.
And this m has a conformal symmetry associated with it.
M?
Over which, can we
M is
last?
Oh, sorry, this thing here?
Yeah, this is something different from the m.
Yeah, sorry, it's a different M. I'm sorry, my bad. This is the measure.
No, it's fine. I just want to know how we are taking the continuum. Is there anything special in the continuum limit? And how do we regularize the parameter?
I think at this stage,
in the continuum.
I think at this stage it's pretty standard. It's a bit like you could look at some book where you do the, in quantum mechanics, where you do the path integral by decomposing it in steps and taking a continuum limit. Yeah. So let me just make a bunch of quick comments, and I see that time is running super fast. So so one comment that I want to make is about the measure. So the measure that you get from this is not a d+1 dimensional diff invariant measure. So while the action part is d+1 dimensional diff invariant, the measure is not. It's not the d plus 1 dimensional diff invariant measure. But it's a measure that's sort of natural from a Hamiltonian path integral point of view, some gauge fixed version of it. And you can go ahead and sort of run in that direction and check, when things are consistent and not anomalous. And you realize that actually the space that you took in coupling space cannot be arbitrary, but it's okay if it's of the following type. So basically you cannot, if you want your full path integral to be d plus 1 dimensional diff invariant, you cannot do an arbitrary path in coupling space, but what you can do is start with an arbitrary profile in lambda and then just evolve it with an arbitrary function of eta. Okay? So this is not the most general thing, but it's enough to achieve arbitrary lambda of x. Okay, and understanding that measure more precisely is also related to Mihal's question about whether this makes sense as a quantum path integral. And since we don't know anyway, it's a bit subtle to try to answer that. The second comment is that it's a bit tricky to understand whether this bulk that we sort of derived or this gravitational path integral is really the real thing, or is it just fake? Because I certainly used large N for the existence of the t-squared operator, but nowhere did I use the fact that the theory was strongly coupled, or in other words, that that the 't Hooft coupling was large. So you can ask, what if I had taken n equals to 4 at lambda equals 5 or lambda equals 13? Okay, that's a large in theory. The operator t-squared makes sense, and I can go exactly through all the steps that I did here, and I would see no problem. So this sort of, makes you wonder whether the bulk that you're deriving is really the real dynamical ADS bulk, or whether it's some sort of auxiliary fake bulk. And again, we don't have a very sharp answer to that question. I think to try to answer it, one would need to study a bit what happens with for example, higher derivative corrections for the t-squared deformation, and that hasn't been done. So okay, there's a lot of things to explore here, and we don't know really the sharp answer to it. Probably the bulk is in general fake, but becomes the real bulk when you're also at strong coupling. I think that's probably the most conservative thing to say. And finally, it gives a perspective on holographic RG, where you can ask, what is the meaning of R max? And here we saw that what we did is we didn't integrate out high momentum modes in the CFT. Rather, what we did, and you can see it very clearly here, is we smeared the CFT, or the CFT metric, over some distance, basically lambda. So in some sense, it is some kind of non-locality because you're smearing the CFT metric, but it's more related to a smearing type of non-locality than integrating out high momentum modes. And this you can see sort of very clearly from the Hubbard-Stratanovich perspective. Okay, that was a couple of comments. I'm basically out of time, so I don't know how much. Will you give me like maybe 5 minutes, Ignacio, to say something about?
Yeah, of course. Go ahead.
Extremal volumes. By the way, I really cut a lot compared to last time I gave the talk, and I still ran out of time. So I guess I need to do more work. Okay, so let me say something about Hartle-Hawking wave functions and extremal volumes. And in the sense of time, let me be pretty schematic. Anyway, I think the level to which we understand this is still fairly schematic. So like I said, the type of things that we wanted to understand is the overlap of Hartle-Hawking of states prepared by the Euclidean path integral with some sources, which are Hartle-Hawking states in ADS-CFT. And so one thing that you can do is take this and flow one side. Okay, first you do it this way. So now you go to some Qij, and eventually flow it all the way down to say like the t equals 0 slice. Okay, and this object now, what is this? Well, let me call it the Hartle-Hawking wave function of the state gamma or the wave function as a function of Qij, which you should think of as the overlap between Qij, some kind of metric eigenstate, and the Hartle-Hawking state or coherent state. And now we can just write down at least a formal formula for, can I please write, yes, thank you. You can write down a formal formula for what this thing is. And it's just basically trying to use our kernel and doing a t-squared deformation on the northern hemisphere, but not on the southern hemisphere. Since you can do things in a spatially dependent way now, in principle, nothing prevents you from doing this. Because one side will stay actually at the ADS boundary, it's important that you use the renormalized partition function and not the bare one. So you do have to add back in the counter terms on the south pole. But now you just take this the solution to the flow equation, and you on the northern hemisphere you do the deformation, and on the southern hemisphere, let me get rid of this. On the southern hemisphere, you basically don't flow it, or you take the limit where the flow parameter has gone all the way to the boundary. Okay, so that gives a way to think about how to compute wave functions, Hartle-Hawking wave functions using this flow parameter, which you can rewrite, again formally in the following way, with some kernel. And this kernel again is just what you get from the flow equation, flowing only in the northern hemisphere. And this gives some sort of nice perspective on how to think about metric eigenstates, is that formally, this is what Qij is. And so Qij is like some superposition over the coherent state. So if you really wanted to take this formula very seriously, you would say that metric eigenstates, what are they? Well, they're these very complicated superposition over coherent states given by this kernel here. Okay, so that's sort of nice. And now you can use this to try to understand something about the volume. The problem is that everything I've said so far is in Euclidean signature. So to talk about Lorentzian, we really need to analytically continue. And so there's a sort of convenient way to do that using York time, which is something that we discussed in a previous paper with Gabor and Aitor. And the idea is to slice the manifold along constant mean curvatures, to use constant mean curvature slices. So to slice it up such that each slice has a constant trace of the extrinsic curvature. And then you go to the slice where k equals to 0, and you continue the extrinsic curvature by sending k to ik. Okay, the problem is that we don't have a wave function with boundary conditions where we fix the trace of the extrinsic curvature. What we have is we have some wave function as a function of the induced metric, Qij. So what we first need to do is do a Laplace transform. Put a big L. So you can do that. The idea is you do a Laplace transform with respect to the conformal factor of the metric. Now you write down a wave function, which is going to depend on if you want the Fourier transform or the Laplace transform coordinate, which is the trace of the extrinsic curvature, and Qij bar, where Q bar is just Q to the 1 over D times Qij. Okay, it's the metric defined up to its conformal factor. And this is just you do the Laplace transform, where theta is basically just the trace of the bare stress tensor. It's related to k. This is like k plus a constant. And you put the Hartle-Hawking wave function as a function of Qij. And you can check that if you want on shell, this gives you the on shell action with now Dirichlet boundary conditions for k rather than Dirichlet boundary conditions for the conformal factor of the metric. Okay, so you can do these set of steps, and semi-classically, this thing simply evaluates to something pretty simple. If you look just sort of on shell, it evaluates to the following. But then this gives you a very, in principle, a very easy way to extract the extremal volume is that you can write down the following. The extremal volume, you just take a k derivative of the log of this thing and then set k to 0. Okay? So I'm going to stop here. This is a formula that you can write down. You need to first, understand how to do the t-squared flow, whether that makes sense, fully quantum mechanically or only classically. You do that for the northern hemisphere, you push it down. Then you do a Laplace transform to really express this wave function, not as a function of the entire induced metric here, but you separate it into metric up to a conformal factor. And the conformal factor, you Laplace transform that conformal factor as a function of k. This gives you the following wave function. And then you take some derivative of the log of it, send k to 0, and obtain the extremal volume this way. So what this does is this gives you some, in principle, CFT way to get extremal volumes. Okay, now there's a bunch of caveats. Of course, there's the question of whether the t-squared flow makes sense quantum mechanically or non-perturbatively. And even if it did, whether doing these series of steps is ever more useful than just solving Einstein's equation and looking for the extremal slice and measuring the volume directly that way. So I don't have a sharp answer, or really even any answer at all to these questions. I think this is a series of steps that you can do. It would be interesting to see if you can really, show that either this makes sense sort of at finite n, and to check if, you could ever compute something in the CFT more directly using it. And of course, to try to see if this connects with more traditional notions of complexity in any way. But okay, I'm wildly over time, so let me just stop here and thank you for your attention.
All right, Alex, thank you very much. It's a very interesting topic. We had a lot of questions already, and in view of time, maybe we can take a couple of last questions if there are.
So I have a naive question. So I understand that the presentation here was quite general, focusing on holographic CFTs. However, what happens if you go to CFT2? So there, I think this factorization problem does not appear.
Sorry, the what problem?
So the problem where we had to factorize, well, this large n limit constraint that you talked about. I think it's, as far as I remember, it's not relevant for CFT2, right?
Yeah, so that's true in flat space. So
okay.
you have other arguments to show that the expectation value of TT bar factorizes in flat space, but it's not known on a curved metric. So actually, there's Yunfeng Jiang here at CERN that wrote a paper about this, trying to establish factorization on curved space, and found some kind of obstructions. So I mean, I don't think there's a no-go theorem or anything like that, but there seems to be very complicated to make sense out of that operator on curved space, even in d equals to 2.
So this finite C concerns propagate there to CFT2, basically.
Yes. Once you're on curved space, yes.
Okay, super, thanks.
It's possible that, on curved space in d equals 2, still the situation is a bit better and you can get away with it, but that you get really screwed in higher dimensions. That I don't know, but I would say at a naive level, it seems to be the same obstructions that happen in d equals to 2 on curved space that in higher dimensions.
Thanks.
Yeah, thanks.
I ask Alex,
Yeah.
I'll start by saying it was a great talk. I really enjoyed it. On this last transparency, you have these nice formulas for the wave function and then the extremal volume. Is it implicit here that what I'm working with is the vacuum ADS, or could you have had your stars and planets and these same formulas still apply?
Yeah, in principle, if you trust the formulas, they apply for any state. So
Okay.
Sorry, I guess I didn't write it anymore here, but there's really a gamma here, which is a label for the metric on the southern hemisphere. But in principle, you could put sources for any operators on.
Oh, okay.
And so, like, to the extent that you can trust this formula, you can do it for anything. There is one caveat, is that the flow equation, we solved it with a diffusion kernel that sort of assumes pure gravity. If you really have, say, gravity coupled to matter, you would need to also show that you get the action for the matter sector.
Okay.
I think this can be done by turning on a source for the matter and taking care of all the fields in the same way and iterating the procedure, but we didn't do that. But in
But if I
principle,
just use stress tensor sources, in principle, I could get something more interesting with some gravitons or something.
yeah, you could definitely try to build stars made of gravitons or something like that this way. You turn on very strong sources for the stress tensor and shoot a bunch of gravitons. They strongly back react. And you should be able to do all of that with this formula if you trust it. Yeah.
Of course I trust it. It's your formula. Thank you.
Thanks.
So for very simple cases like global ADS, 3 dimensions, CFT2, is it easy to see how this extremal volume formula can be used to recover the known results? I guess I'm trying to understand how easily can I use this formula for.
You're trying to ask, what you're asking is there any situation, even just the vacuum or something like that, where I can?
Yeah, very simple systems. I just want to compute.
I'm not completely sure. It's in general, it's very hard to solve exactly for these like Wheeler-DeWitt wave functions. So for example, Pavel had like a couple of nice papers on trying to just looking at a mini superspace thing where you assume spherical symmetry and then you find the function exactly and it's the Airy function. The problem is that trying to do these weird flows where you flow in just the northern hemisphere, you'll definitely break any type of mini superspace. So actually solving for these functions seems very hard to me. I don't know how you would do it. Of course, you can do everything in the semi-classical limit, and you can tell yourself that you're doing a CFT computation, but what you're really doing is like going into the bulk and solving Einstein's equation. So that's why I'm saying it's not clear that this formula ever buys you something useful that you can do in an easier way by solving Einstein's equation in the bulk. It would be nice if one could check that, but yeah, if your question is there any example where you can check it?
Yeah.
I think the answer is for now, no.
Okay, thanks.
Hi, Alex. I have 2 questions. Can you hear me?
Yeah, I can hear you. Yeah, I can't see you.
Okay, I'll turn on my camera. So thanks for the nice talk. I have 2 questions. The first one is like a following up with Rob's question. If you include some matter contents in the bulk side, for example, some Maxwell field, then what do you expect that the extremal volume will, like how the extremal volume formula will be changed with those matter contents?
Yeah, so this is kind of what I was saying before. I think it won't really. So it will in the sense that this will come from the kernel will be different, because now the kernel will not just be the gravitational path integral, it'll be the gravitational path integral plus the matter path integral. So you have to assume that you turn on sources for the matter fields, and then you have to rederive the kernel in the full theory with the matter, and then this will now be a solution to that flow equation with the matter. So we haven't done that, but honestly, I think like this would be a straightforward exercise to just add a scalar field, for example, and compute the kernel there. Yeah.
Thank you. The second question is, like you said something about in your work, you understand the two derivative in the Wheeler-DeWitt equation and the one derivative in the flow equation. Can you make some more comments about this part? I'm interested in that.
Yeah, so this is sort of a very general thing, is that when you look at the flow equation, its first derivative with lambda, but second derivative with respect to the metric, right? So if I'm saying a solution to the flow equation is the same as the solution to the Wheeler-DeWitt equation, that seems a bit problematic, because the flow equation would need one piece of initial data. It's a first order differential equation. The Wheeler-DeWitt equation is second order. It seems like it needs two pieces of initial data, right? And sort of the way that you resolve this is by realizing that it's the solution to the Wheeler-DeWitt equation, but sort of on a constrained set of initial data, if you want. And there's really there's a very nice analog that you can make just with the diffusion equation. So I didn't have time to do this in the talk, but in our paper, we actually write the diffusion equation, dx squared and dt squared and some potential, and dt and some potential. And you can see how all of this comes about. It's that, the initial data that satisfies some additional scaling symmetry reduce it basically to first order ODE. That's the way to think about it.
Okay, so you mean that the moduli space for the parameter is constrained to only the scaling invariant parameter? Does it mean?
If you want that, yes, you can say that way if you want. Yeah.
Okay, thank you.
Yeah, you should look at the paper, and the example I think is very clear. It's just a 1D-PD, so 2D-PD, so it's pretty simple.
Thanks.
Okay, Alex, so I think there's probably many more questions, but I think in view of time, we should thank Alex again.